Hello student, welcome to the web optics course. Today we have lecture number 49, and in this lecture we will going to discuss about Fresnel diffraction for an rectangular aperture. So we have lecture number 49 today. Before going to the rectangular aperture, let me go back once again to the circular aperture that we had done in the last class. So our problem was we have a structure like this, and then we have a circular aperture like this, and then we have a screen here, and try to figure out what was the intensity at this point over z axis. So this is my small x, small y, and this is z equal to 0, but this is z equal to some point z, and we calculated in the last class that for this system, if I want to find out the intensity at the point over this z axis, this intensity was I, which is calculated over this z axis. So 0, 0, z, that is something I naught and sine square pi by 2 p, a parameter called p, where the parameter p was a square divided by lambda z, where z is a distance and a is the radius of this aperture, and lambda is the wavelength. So that was the expression, final expression we got, that what is the value, and then we plotted that. A typical looking plot was there, and the plot was I divided by I naught. So that is why this value was, and then we plot as a function of 1 by p, not p but 1 by p, to show how it changes as a function of z. And then we have a maxima and minima, then maxima and minima, something like this we got. Now let us go back to this problem and try to understand these things. Last day we tried to discuss this. So suppose this is the aperture we are talking about, this is the aperture, and this is z axis, and this is the point p, this is the point p over z axis, and this is p. Now this, if I join this, so this is 0, or O, and if I join this, then this is the value A, which is the radius of this aperture, and this point if I write A, then we can have a relation AP square of that is equal to A square plus OP square, which is our Z. So, essentially it is Z square. Now, A is much smaller than Z. So, with this I can write AP is nearly equal to Z plus A square divided by 2Z. The usual relation we use. From here we can write AP is equal to Z 1 plus A square Z square whole to the power half, and then we make a expansion of these things and we are going to get this under the condition that A divided by Z is much less than 1. Now, if I want to find out what is the path difference between AP and OP, then AP minus OP, which is nearly equal to Z plus A square by 2Z minus Z, then this value is essentially A square divided by 2 of Z. Now, if this aperture according to the Fresnel's theory, if this aperture contain n half period zones, n number of half period zones, then this path difference, whatever the path difference we have, that is AP minus OP that should be equal to n of lambda by 2. This is according to the Fresnel's theory, and this value is simply A square divided by 2 of Z. So, from this calculation what we get is very interesting, and that is n, the value n, which is a number of zones, is equal to A square divided by lambda Z, which is essentially equal to the parameter P we already defined during the calculation. So, what we get in the previous calculation, P is essentially represents the number of half period zones. So, P essentially represents the number of half period zones that is contained by this aperture, whatever the aperture we have. Now, note that the intensity distribution was related to this number. So, it is I naught sine square pi by 2 then P. That was the relation we got. Now, we can see from this expression that when P goes to 2, 4, 6 etc., then that means the aperture, which essentially means that when this is 0, then I is essentially 0. So, let me put that first. I is essentially 0 under that conditions, and for that actually that means the aperture contains even number of zones, and which is true when the aperture is contain even number of zone, then this individual zones will cancel out their individual contribution, and essentially we get a very low intensity, and that we also get from this calculation. When again when P is equal to 1, 3, 5, then I is equal to I0, which is the maximum value. So, that means here the aperture contain odd number of zones, and we also calculate from that the radius of the n half period zone of the nth half period zone, that is Rn square divided by 2z, which is nearly equal to n lambda by 2, and Rn from here we can see that Rn, which is already calculated is root over of n lambda z to the power half. So, that was the radius of the nth aperture. That means if P is related to the number of zones and P is a square divided by, so P is here a square divided by 2 of z, that is this A. So, if I move this z, if I reduce this z, then P will going to increase, and if P increase, that means number of zones will going to increase. If the number of zone increases from 2 to 4, then what happened, we will going to get a consecutively a dark and bright fringes. Z decreases if I go to this side, then P increases, but if I go to that side, the Z increases, P will going to decrease. So, I can get the value of the P value from some value to it is decreasing. So, we will get either integer or in certain points either 1, then 3, then 5, then 1 if I go in this side. So, that means P is increasing 1, and if you then we get 2, then 3, then 4. So, this value gradually we this value will going to change, and each point we have a different intensity. In one case it is maxima, in another case it is minima. Exactly the same thing we calculated by expanding the theory, where I get the intensity is really changing with certain function, and this function reads this with that value of P. So, these things are correlated to each other. Here P, during the calculation we got the value of P, but P is essentially the number of zones that one can have for a given Z. So, that is the thing I wanted to discuss today before discussing the diffraction for rectangular aperture. So, let me go back to today's calculation, today's topic, that what happened for a rectangular aperture. So, the aperture is now not circular, but something like this. And we have like before, we have x and y coordinate, and we have a screen here, and then due to this aperture we try to find out how the distribution here one can expect with a different coordinate. Different coordinate big X, big Y. Now, before going to this calculation, we need to know few things, and that we will first introduce, and the thing is called the Fresnel's integral. Fresnel's integral, and this Fresnel's integral by definition suggests curly C, which is a function of nu, is equal to integral 0 to nu cos function pi by 2 x square dx, that is the Fresnel's integral by definition, we call it C, and another is S, curly S, and by definition it is 0 to nu sine pi by 2 x square dx. So, these two integral are called the Fresnel's integral, and this is by definition, that is the function. Now, if I look carefully to this function, few things that we can comment, and that is the integrals are even function of, so these are even functions integrals are even functions of nu. So, I can write C of minus nu is equal to minus of C nu, and S of minus nu is equal to minus of S nu. That is the relation we have. Also, I like to show these things, that is the integral, part of this we have already shown. So, minus infinity to infinity e to the power of minus mu x square dx is essentially root over of pi divided by mu. From the knowledge of gamma function, one can do this integral very quickly, and they can understand very nicely how this integral have this form, but this is the value of this integral. Now, if that is the case, we can write it as minus infinity to infinity e to the power of I pi by 2 x square. Then we have dx, that value essentially should be pi divided by minus I pi by 2, or it is root over of 2I. If I multiply one I in the denominator and numerator, then this value minus I into I will become 1, pi will cancel out, so it should be 2I. Now, this 2I is essentially root over of 2, then e to the power, root over of I is written by e to the power of pi by 4, and we have root over 2 1 by 2 1 over root over 2, then I this, which is essentially 1 plus I. Now, if I look in the left hand side, then left hand side is interesting, because left hand side gives us this if I expand this gives us the value of Fresnel's integral. So, let me do that. So, minus infinity to infinity e to the power of I pi by 2 x square dx, that is essentially 0 to infinity e to the power of I pi by 2 x square dx, and that quantity, if I have, it is 2 0 to infinity cos of pi by 2 x square dx plus I integral 0 to infinity sin pi by 2 x square dx bracket close. So, essentially this is 2 and this value is Fresnel's integral C nu, and not nu because here the limit is infinity. So, it should be C infinity. This is the identity we are doing here, C infinity plus I S infinity, and that quantity is essentially equal to 1 plus I. So, that means if I write it, C of infinity plus I S of infinity, that is essentially half plus I of half. So, I get a value for this integral, extreme value C infinity is equal to half and S infinity is equal to half, that is one set. Another also, C of 0 will be 0 and S of 0 will also be 0. So, this identity we show in today's class. I do not have much time to go beyond that. So, I will in the next class I will start from here and try to discuss more about this Fresnel's integral, and then what we do, we are going to exploit this expression to find out what is the intensity distribution, how the intensity distribution look for a rectangular aperture. With that note, I would like to conclude here. Thank you very much for your attention. See you in the next class.